Let's get started. How many of you before have ever gotten shocked? Literally, just shocked by something. Yeah, right? It's like a weird feeling. How many of you actually got electrocuted? Actually electrocuted. What was the scenario? Give me a background. When did you get electrocuted? How do you know you were electrocuted, not just shocked?
I know it's electrocuted because my mom forced me to go to the doctor after I was a young kid.
Okay.
I was with my cousins. We were playing house, and so I want to say it's like it was bigger than a bobby pin. You know, like the clips that they put on clothes. So we were using those, and they were metal. And my cousin goes, "Okay, so like use that," which was like an outlet, and she was like,
Yeah.
"The key in the door to open the door." And I was like, "Oh yeah, like that makes sense." And I did it and got electrocuted. And my mom freaked out, ran me to the doctor, was like, "Tell me my kid's brain's not fried." He was like, "No, she doesn't electrocuted. She's not messed up, she's fine."
So you were a kid, so you probably don't remember the feeling of it as much. Stop, that's mean. I was dropped on my head. I know. I was dropped on my head as a baby on a tile floor, cracked my skull, had to go to the hospital. I was like 2 months old. True story. Tell me about yours. Do you remember? Are you older, younger?
It was like 2 years ago.
Okay, what was it? Go ahead.
It was like less severe like that. It was something like I was plugging in my laptop. Like I guess my finger was too close to the...
And you just got to...
Yeah, I just felt it for like maybe 2 seconds.
Okay, so that wasn't that bad at least. That's good because you were probably actually touching the rubber wire too, so you were able to actually remove your hand. A little jolt in your arm, right? Yeah. So I was electrocuted when I was younger. I just dropped my head, electrocuted. I was like 10 years old, and I was going down to the basement, and my uncle and like a bunch of others were renovating our basement for us. He does all this construction work. So I was a kid, and I didn't realize like, oh, they're doing all the work down there. I had to go get something from my dad. He's like, yeah, go down there. So I turned to go down there, and I went to reach to turn the light on. But if you remove this plate, what's behind lights? It's wires, right? And 2 lead wires that actually accept or connect to this actual receptacle, whatever you call it. And the 2 wires, if touched at the same time, can cause electricity to flow through your body because you're completing the circuit. We're going to do a lot with circuits in the next chapter, but it causes you to allow electricity to flow through you. Well, your electrical system in your body tenses up, your muscles start to spaz. That's why if you get electrocuted, sometimes it's hard to pull your hand away. And people can die from that. For me, I was lucky. I was going downstairs. So when I got electrocuted, my body naturally started to shake, and I couldn't, but my body was falling forward down the stairs. So gravity overcame the electric force that was holding my arm there, and I fell down the stairs, which was actually a good thing, not a bad thing, because that's what actually got me to remove my arm. If you've ever seen like stories of people getting electrocuted, and you try to help them, what's going to happen? Yeah, you're going to get electrocuted. So if he's actually attached to something, you're like, yeah, no, you try to push the person off, the actual charge can go through your body. Realistically, you should take an object, but would you be thinking at that moment to do that? Probably not. Probably not. Now, the best thing would be like tackle them, because your inertia, your momentum will carry you and the person and disattach them from the wire. That's what happened with gravity for me. Gravity pulled me away from that wire. Brian and Carolyn.
I think that happened to me this summer because I remember my dad wanted me to hardwire, what's it called, the sprinkler, the pump into the house, so we could actually flip the switch in the house to turn the sprinklers on and off. So he wasn't able to get on the deck, so he had me go on the deck, and he was trying to explain to me to not do that, and in the middle of him explaining to me not to like touch both the wires at the same time, or like not touch the very tip because there's not a lot of rubber on it. I got like electrocuted, and then I just stopped because I was like shaking.
But you felt like your muscles tensing up, right? Yeah, it's a lot of the charge is so much that's going through your body that's what's causing it. Carolyn, you're gonna say something though too.
Yeah. Over the summer, there's like 2 beach clubs in Breezy, and one of them my friend was a lifeguard at, and she he was working on duty, and a little girl went down the slide and she got electrocuted somehow on the slide, and we have like a contract as lifeguards that we have to save them. If we're able to save them, we have to. So we dove in the water and touched her and got electrocuted, and they both went to the hospital. They were fine.
How did she get electrocuted?
There was something wrong. There was like an electrical shortage at the top of the slide, and since the water like jets were going out, like she stuck her hand like in the jet or something and went down.
Oh my
And
gosh.
she like couldn't move, so he dove in the water and like got her, and then he got electrocuted.
Scary.
Yeah, with all the water.
I'm guessing that it was the slide, the water that was flowing in, that was electrical. But if there was enough distance between the pool and the actual slide, it's not going to carry the electric charge into the pool itself.
Does it take? Does a taser? Is that the same thing?
Yeah, that's exactly what it is.
I was gonna say.
But it's low voltage. So we're going to talk in a moment about what charge is, how much charge is physically there, and that's very low charge in a taser compared to like lightning or actually electricity coming out of the wall. But that's exactly what it is. It's compared. Good?
Yeah, you're good.
And is the probe reading? Is it getting a good reading? Give me a second. Can you go to my office and grab my laptop? I'll let you log in and connect because I want to display it up here.
Wait, so getting tased isn't technically getting.
It is, but it's a low amount of voltage. That's all it is.
Guilty.
Low amount of voltage.
You survived.
I don't want to know why I've been tased.
You survived the lightning bolt.
People have, absolutely. Yeah. People have survived lightning strikes. You know why? What kills you when you get struck by lightning? Anyone know? Heart stopping. So, believe it or not, if the lightning goes to your body and doesn't pass by your heart, it won't cause your heart to stop. So you can survive a lightning strike. There are stories of that. But do you normally? No. So much voltage. We'll talk about how much charge it is. That's actually one of the examples I'm going to give you is a lightning bolt.
You know, like those things where they bring you back to life?
Yep. That's exactly what it's doing.
It stops your heart?
It
resets your heart?
It's jump starting your heart. Defibrillator.
What is it?
Talking about defibrillators, right? Yeah, it jump starts your heart. That's what it's actually doing. But your heart, so your heart actually, your body has electrical impulse to it. There's electricity flowing through your body right now. Every time your heart beats, there's an electrical signal that's actually carrying. So to start your heart up again, you need that electrical signal. That's what's happening. So it's jump starting your heart. It's the opposite, or it's similar to this, but it's the opposite direction. Is it number 5, you know?
Let me check.
Number 3.
Yeah.
What's the Wi-Fi on the bottom of it say? Anything? Is it connected to Wi-Fi?
Not connected, no.
Tap that little Wi-Fi guy. Does it give an option of like...
Yeah, join oil ADS.
Is there no one? Hold on, I give you the password.
It's a hot summer day. Clang, bang, cow. Wait, that's the elevator stopping at my floor.
Wait, Nick, do you remember Brianna's
There you go.
speech about the
So-
microwave?
Username and password again. So like, I need to see
We could have the refrigerator and just like buzz.
Why did you do that? Right in the beginning, right?
It was so bad.
Let's use one of the five. Or maybe one of those computer and you manuals type your name on the computer.
Why did they wait?
Try to get your person to know. Well, the computers in this example, it won't show up. So you have any manual addition, all caps, no space. All right. While Anthony's setting something up for us, while he's doing that, let's continue this idea. So, yes, Ernest.
So for the flash, like, when you struck by lightning,
For the
did
what?
it- like for the flash, like did his heart stop or did it just
For who?
the flash? When the Flash.
Superhero, the Flash?
Yeah.
I don't know how the Flash became the Flash. How did he become the Flash?
Oh, it said he was struck by lightning.
Oh.
Science behind
I don't think there's any valid science behind what they're trying to get out there. I'd have to read a little bit more. I'm not sure. Mr. Hall would know that for sure, though. I know he loves like the Flash or like any sort of comic. I do too, but the Flash was never something I was into.
it. Oh, okay.
I was always reading about Batman, Superman. Those are like Wolverine. I liked. All right, let's go to the next slide. So, hey, let's talk real quick. How can you get electrocuted? Physically, what's happening? Physically, what's happening when you get electrocuted?
Electric charge is being transferred to you.
Yeah, good. I like the word transfer. The electric charge is being transferred. It's not being created. It's not like suddenly you're like, oh my gosh, there's electricity. It just came out of nowhere. It's transferred. It was there all along. electric charge is conserved. Let's jot that down. Just like energy. Remember conservation of energy, conservation of momentum. Well, those things, if you think back to, that meant that the energy before equaled the energy after. So as a result, it's working perfectly.
Okay,
As a result, the charge on a certain object, give me a minute, I'm having to do it, okay? The charge on a certain object can only be gained by transfer of, in this case, take a look, electrons. It's all about the electrons. Why is it not all about the protons? Who could explain? There's a lot of chemistry involved in today's lesson.
The electron is carrying the charge.
Okay, that's kind of recreating what we're saying, but I said, why is it not the protons? Why is it not the protons? Think about your chemistry, guys. Come on. Ernest.
Because they're positively charged.
No. It's nothing to do with the actual charge itself. Why are the protons not the things?
Well, aren't electrons located outside of
Oh,
the
yeah.
nucleus? So like if for something to happen, like a connection, electrons must react with other electrons.
That's exactly right. Guys, come on, stop. It has to do with, she's talking, you guys are talking under your breaths. It has to do with the fact that electrons are in some sort of a cloud. We talk about in chemistry shells. Shells are like a really simple way to look at it. It's not the true way electrons actually are. They're in a cloud. And the concept is that they can be at certain locations at different times. If they're moved to a different location, they've gained or lost energy. If they move back down, they gain or lose energy. What is going on, guys? All for a stylist? Next time, just get up and go get it from me. The electrons themselves, though, can move. Why can't protons move, though? Answer that question. So you answered why electrons can move, which is good. Why can't protons move? Where are they? In the nucleus. Come on, guys, this is like chemistry 101, the most basic. Protons are in the nucleus. In the nucleus, you have protons and you have neutrons. There are forces that occur in the nucleus that hold it together. Do you remember van der Waals or weak force or strong force? The nucleus itself is not splitting apart anytime soon. If it does, you got a problem. A lot of energy is going to be released. That's called nuclear fission. When the nucleus splits apart, a lot of energy is released. A fission bomb is exactly that. So when you break apart a nucleus, there's a ton of energy holding it together. The electrons, though, they're like, we're just hanging out. We can go from place to place. We're commuting back and forth between different atoms. So when you take a balloon and rub it in your hair, those electrons jump from either your hair to the balloon or balloon to the hair. One object to the other. So, if there's an overall charge on something, let's use that as the example. Okay, you take a balloon and you rub the balloon against your hair. I forget which way the electrons move, to be completely honest with rubber here. It really doesn't matter in this case. But what I want you to see is this. Let's say that rubbing your hair, the balloon gains 7 electrons. 7 is such a small amount that it will have no significance. So it would be more. But let's just say for the sake of today, 7 electrons. That means that the charge would be negative 7e. It gains physically 7 electrons. Well, what does the hair do? Where do the 7 electrons come from? Right? Not the air around you. You rub the balloon against your hair. The balloon gains 7 electrons. It gains 7 electrons. Your hair then loses 7 electrons. Conservation of energy. Conservation of charge. Conservation of momentum. All similar things. So for your hair, you would write this. Now, this is very, very easily misconstrued as, oh my gosh, look, your hair gains 7 protons because it's positive. Your hair is not gaining protons. Protons are not moving. Electrons are moving. So if I said something had a net positive charge, what does that actually mean? It had a net positive charge. It means it lost electrons. Is that clear what I'm saying here?
Yeah.
Just because you have a positive charge, you didn't gain protons, you lost electrons. It's the same thing, right? If I lose electrons, it just means now I have 7 less electrons. So I've got more protons. So I've got a net positive charge. All right, before we go further, Anthony's set up this entire experiment for you nicely over here. Now, what we're going to talk about in a minute is called charging by contact, which is what you're seeing here. So what Anthony did, nice, got himself grounded and everything, good. So he grounded himself, so he's not going to get electrically charged. There are two rods here. These rods, actually there's a couple rods here too, so there's a few of them. These rods can be charged simply by rubbing them together by contact. These rods can be charged by taking wool or the cloth on them. Now, what is the name of the apparatus again? What's it called? Yeah, Faraday. So this is called Faraday's pail. Faraday was a famous scientist that did a lot with electricity. It's called Faraday's pail. And what it is in the inside here, this is an object that actually can lose or gain charge based on bringing something in its proximity. Now, this is a rubber mat, so it's grounded. He's grounded himself, so he's not electrocuted. And then there's a probe here that's hooked up that measures the actual electrical charge. So, which one are you going to do? You're going to do the two materials or the cloth? Whichever one works for you. Second one.
I mean, both of them worked. I can just do let's do this one.
All right. So before you do anything, Ann, let me switch over so everybody can see. Take a look at the board real quick. So, is there a way to calibrate the sensor? You zeroed it? Okay, there you go. So you just zeroed the sensor. So what is this unit again? What does that mean again? N? So first of all, C is Coulomb. Sorry. Go back real quick. C is Coulomb. That's the unit of charge. Like Newton. Coulomb is the charge. So this is Coulomb. What does N stand for? It's a prefix. Like millimeter. N was what? Nano. Times 10 to the negative 9. So I want you to start with recognizing this is a minuscule charge. 0.09 times 10 to the negative 9 coulombs. It's a small charge because electrons, we're going to see in a minute, are even smaller in charge. That's a side note. So Anthony is currently rubbing this actual thing, which is giving it a charge. Now when he brings it into the pail, take a look at the value up here, what's going to happen. So suddenly the pail is recognizing 7 nanocoulombs of charge. Where are they coming from? So we're moving now ahead. Where are they coming from? The cloth that he was holding, the electrons jumped from the cloth to the rod. How do I know that? What did the charge become when he put it in? It became negative. So because this becomes negative, now there's an abundance of electrons on that rubber rod itself. Does that make sense what happened there? That's the simple experiment for this one. Did you get any further to the others yet or not?
They have these.
There's a way to do it where you can rub them and then charge by grounding and stuff, but it's a little more difficult. Did those? Yeah, see how those work.
I think it was you put in the white one.
Yeah, there we go. So we see that the white disk, its electrons jump to the other disk, so the white disk has a net positive charge. Again, it simply means it lost electrons. Okay? The reason I do this demo at the beginning of the year is to prove to you guys or show you how small charge actually is. So we're going to get to this in a minute, but you recognize again, nanocoulombs, nano. So we're talking 0.0003 coulombs. So 1 coulomb is actually a good amount of energy. Okay, we're going to talk about overall net values in a minute now. And you can leave that set up.
Okay.
Because I'm going to take a look at it later today to work on something else that I can work with.
All right.
Thanks, Ed.
Isn't one of the colors that comes from it, is that like the color of the,
Like that yellow color?
I don't know. I don't know, where does that color come from?
It's probably, honestly, what did we just study? Refraction. It's probably refraction. So it's also probably the molecules in the air. So when lightning strikes, right, it has to do with an imbalance of charge. So if there's an imbalance of charge, the actual charge wants to go from one area to another. The Earth is a giant grounding source. So all that extra charge wants to go to the Earth. That's why it strikes the Earth. When there's heat lightning, it goes from cloud to cloud. There's an imbalance of charge in both clouds. Now, when the lightning actually goes through the air, it's affecting the molecules around it. So it's got to be some sort of an interaction between the actual electrons and the actual particles in the air. Not sure of the exact answer, to be honest, though. Yeah, of color.
Makes, like, you know when you rub the balloon to your hands and it sticks? What makes it stick?
Okay, so that is similar to what he was just doing.
Yeah.
So when he was rubbing those two materials together, one of them was gaining electrons, so the other must have been losing. So now we're going to talk about opposites and what do opposites do when it comes to electric charge. That's why. So your hair loses or gains electrons while the balloon gains or loses. So one's positive, one's negative, right?
It's like a magnet.
Exactly. Electric charge, as far as positive and negative, we can write this down. Likes repel, opposites attract. Just like magnetism. Okay, just like magnetism with poles, north and south poles. Likes repel, and opposites attract. All right, so let's talk about some numbers real quick so you have an idea. I don't usually do this. I usually say like, all right, a kilogram is around 2 pounds, so at least you know what a kilogram is now, right? Because you understand what a pound is. Can you all physically understand what a pound is? Right? If you've ever lifted like a 2-pound dumbbell, you understand what a pound feels like. So if you think about a 2-pound dumbbell, that's about a kilogram. So the mass of a kilogram, you can at least estimate it. But can you really physically understand what a coulomb is? Not really. That experiment helped a little bit to understand that coulombs are the energy transfers are really small amounts of coulombs. But let me give you some numbers so you have an idea. So the first one is usually, if you think about like rubbing your feet on a carpet. Ever done this before? And then you touch something that's grounded, you feel a little shock. That's on the order of microcoulombs. So that's on the order of microcoulombs. What does micro mean? What prefix? Micro, 10 to the? -6. So we're talking about a very small amount. Again, 0.00001. Okay, we're talking about a very small amount of coulombs of charge. If we take a look, I think I'm adding a decimal there. 1, 2. Yeah, added a 0. Get rid of one of the zeros. If we take a look now, so that's just simple, right? That's just rubbing your feet or rubbing the balloon on your hair. That's how much charge you're generating. Very small amount of charge, just like Anthony showed us with that experiment just there. The second scenario I'll give you, a lightning bolt. A lightning bolt is between 15 and 350 coulombs of charge. So just compare those two. Yeah, you think when you charge your feet up on the rug and you touch the wall, you go like that, right? Like, ooh, it's a little shock. Feels like it's like something. It's nothing compared to a lightning bolt. Compare 0.001 to 350. This is so much larger, it's incredible. So when a lightning bolt strikes, we're talking about a whole lot of energy or a lot of charge. Okay, a real lot of charge. Now, yeah, Jake, Ed. What is that the question? I don't know. Check it out. Google it for me. That's a great question. I don't know. The other class, somebody asked, or was it one of you guys that talked about the defibrillator already? Or was that, it was you, Lieutenant, jeez. I think it was right before this, sorry. But the defibrillator has like the exact right amount to get your heart going again. And you know how it does it? It reads your pulse. The defibrillator is not constant. So depending upon what it's reading, it actually can send more or less charge to get your heart jumping or going.
What if you don't have a pulse?
It's going to send the most possible.
Does it hurt to get struck by lightning, or would your body just talk like you wouldn't feel it?
I mean, I'm guessing if you died from it, it would happen so quick you wouldn't feel pain. Think about it. The lightning travels at what speed? Yeah, the speed of light, close to, because it's in the air. It's a little less, but close to 3 times 10 to the 8. So by the time that lightning passes through your body, you haven't even registered to hit you. Right. Lightning strikes. If you get hit by lightning, it'll hit you before you see it. Put it that way. You won't even see the lightning before you're dead. So will it hurt? I don't know, but I'm going to guess no, because you're dead. But if you survive it, if you ever looked at lightning survivors, what do they have at the bottom of their feet?
Oh, like the black marks.
Burn marks at the bottom of their feet. Why? Goes to the ground. The earth acts as a grounding mechanism. Lightning wants to go to a sink. A sink is a place where it can absorb all that energy. The energy needs to go somewhere. Well, if it's all this extra energy, it's going to flow right into the earth, through your body, into the earth. Right?
Yeah, they also do like weird lightning marks usually.
Usually, I would guess on the bottom of the feet, I know for a fact.
Like, I know that, like on your arms or your back or something, that have like these weird marks. That looks like.
Well, sometimes that's like your veins.
You're saying like where the lightning enters you, or you're saying as it travels through your body, you get marks in the body?
Travels through your body.
It's very possible. I don't know. That's a good question. I love that we have Google nowadays, right? And I was like, yeah, check it out. I'm not really sure.
I read somewhere like you can kind of tell if you're about to get struck by lightning
Well, first of all, elevation is definitely a big deal. That's why when in like a lightning storm, lightning rods are at the top of a tower. Lightning rods are there on purpose so that there's a lot of metal. Metal's a good conductor. We're going to learn in the next slide. So the lightning naturally gets gravitated or attracted to the metal because of the height. That might be why they tell you to crouch down. I don't know. That might just be a myth because honestly, the lightning's going to strike you before you even know it's being sent. So how do you have enough time? Like, you know what I'm saying? Like the time it takes you to crouch is longer than the time lightning takes from coming to the sky to you. So I feel like that wouldn't be possible. I don't know. Jake and then Gabe.
Well, I know for fact, like, it might just strike close to you, like, it just blinds you, because, like, when I was, like, 11 years old, like, I was walking through my front yard, and a lightning bolt just, like, struck down on one of our bushes and just completely fried it, and I was, like, maybe 5 feet away, and it just, like, blinded me for a second, I just couldn't see, so.
Makes sense. I mean, think of like a camera flash, like really quick, but much more high intensity. Gabe?
Like I Googled it, it was like
Oh, wow. That's incredible.
I don't know if this one's real.
That looks like that looks like a tattoo over there. Yeah, look at the marks up on this guy's body, on his arm, on his back. It looks like almost like a tree, like the tree limbs. Really interesting. It probably is outlining your nervous or electrical system in your body. Your electrical system is like branched. It continues and it connects all throughout your body. So that's probably the outline of what that is. That'd be my guess just by looking. I don't know. Hey, the last one I want to show you about. So that was a lightning bolt. So we've got just rubbing like on the carpet first, then a lightning bolt. The last one is the amount of energy in a battery over a lifetime. Believe it or not, a little simple AA battery that you would put in your remote control has a lot of charge in it. Over a lifetime, it will dissipate 5,000 coulombs of charge. Not all at once, though. That's the difference. How many of you, raise a hand, have ever taken a 9-volt battery and touched it to your tongue? Do it. All right. So, yeah, it doesn't hurt. It doesn't hurt. A regular battery, like a AA, it doesn't work with a AA. It's got to be, you know the square ones? 9 volts, the rectangles, really? They have both terminals at the top. If you ever looked at a 9-volt, both terminals on the top. And AA battery, one terminal's on the top, the other one's on the bottom. So you can't really fit your tongue around a AA battery, so I wouldn't do it with that one. Take a 9-volt battery and touch your tongue to it. You'll feel the electrical current, because your tongue is a conductor. You'll feel the electrical current flowing through your tongue back into the battery. And if you hold it there long enough, you'll start to get like an acid taste in your mouth. It's actually the electrical charge like kind of messing up your tongue. If you held it there for like days on end, you would have acid burned like crazy on your tongue. So when I say do this, I mean for like 3 seconds do this. Please don't come in Monday with burns on your tongue saying, oh, I did it, look at this. Literally, like, it's not going to hurt you if you do it for a couple seconds. If you hold it there for a couple hours, it's going to hurt you. But what's happening is this. There's a small amount of coulombs that are being moved. But over a lifetime of a battery, it actually uses up a lot of charge. 5,000 coulombs of charge. Why is lightning so dangerous? Because you're getting all 350 at once. That's why it's dangerous. A battery, although having more charge than a bolt of lightning, all the energy in a battery is not suddenly going into it at once. It's only a little bit of energy that's flowing to the battery. A battery is made in a way that regulates the amount of energy that's flowing in and out of it at one time. Okay? You're not getting, because think about it. If a battery, right? Okay, I take a battery, put it in a remote. I go to watch TV. I press a button to turn it on. If all the energy in the battery used at once, would it make sense? You'd have to replace the battery every time you press a button. So what's happening is that a small amount of charge is being used or transferred or dissipated every time you press a button. So over time, the batteries drain. But if you've ever used remotes, you know that how often do you refill the batteries or change them? How often?
Every couple months.
Yeah, a couple months. Some batteries, if you get like the long ones, a year. My dad goes to the dollar store all the time. He's retired, he's on pension now, or not even pension, he's on senior citizen, whatever, what is it called, Social Security. So he's at the point in his life where he's just like really cheap, I'll be honest, it's the truth. I love my dad to death, but it's what it is. So he goes to the dollar store all the time now. It's like, yeah, you get so much at the dollar store, it's great. I'm like, okay, Dad, but if I take a voltmeter and hook it up to this battery, it's got very little, he gets batteries at the dollar store. They last like 3 days, 4 days. I'm like, Dad, go get Energizer batteries for $3.99, 2 of them, and they will last you a year. Instead, he's paying $1 for like 50 batteries. I'm like, Yeah, but you have to change them every 2 days, not 2 days, but every like 2-3 weeks, whatever it is. But it's because it's where he's getting them, you know what I mean? So it depends on how much charge is in the battery to start. So when you see batteries that are really low cost, like that was a mistake. I once bought like 100 AA batteries on like Groupon or like Woot.com because it was a crazy sale, I remember. But the batteries died so quickly because there was very little charge in them. So you're better off putting your money into something that has a longer lasting lifetime to it because there's more charge in it. But generally speaking, not as much charge is in an actual battery. Okay? All right. Let's get to the next thing. This next thing is really, really important. This is like the fundamental thing that tells us about how energy is transferred. It's the charge of an electron. So, anybody remember the Millikan oil drop experiment?
I love water and oil.
Millikan oil drop experiment. So, pretty much, it's going to take a while, probably on Monday before you guys do your project. I'll give you a little video of that or something. Pretty much, here's what happened. This guy, Millikan, and his assistants, really his students, are the ones who really came up with this theory. He just took the credit. Happens a lot, by the way. Newton stole a lot of his info, by the way. Newton was mad smart. He really was. But his students, a lot of them were smarter than he was. And they came up with a lot of the theories and ideas that he actually proved true. But he got the credit for them because he was the professor. So this guy, Millikan, had this idea or used an idea of someone else. And he pretty much came up with the concept that he could find the charge on these oil droplets based on a certain amount of energy between two charged plates. But what he came up with as an overall conclusion, besides how it worked, was that the oil droplets were charged. And when he looked at the ratings on them, here's what the numbers look like. And I'll write them down so you can see. What do you notice? Anybody pick up on it? You have to have decent math to pick up on it, right? Increments of 1.6. These are all multiples of 1.6. So what Millikan was able to discover was that anything that was charged at all, was always a discrete amount. What does discrete mean? Specific, how about? Discrete versus continuous in your math course? Discrete is like 1, 2, 3, 4, 5. Only integer values are discrete numbers. Continuous is like 1 through 5 with all numbers in between. 1, 1.001, 1.002, 1.003. No increments at all, really. Any number between 1 and 5 is continuous spectrum. Discrete means every individual number itself. So he recognized that there was a discrete amount of charge on all of the droplets. And they all happen to be multiples of 1.6 times 10 to the negative 19. That's what came up with the charge on an electron. So an electron is simply this charge right here. That's an electron charge with a negative in front of it. E is the fundamental charge. It can be positive or negative. Electrons are negative 1.6 times 10 to the negative 19. So earlier, when I was talking about rubbing your hair with a balloon, and I was trying to tell you guys, I was like, it's a really small amount of energy. Right? When you rub your hair with a balloon, it's like this. That's how much energy you're giving it, or charge you're giving it. Well, take a look. An electron is even smaller than this value. An electron charge right here is way smaller than that value. So when you rub your hair with a balloon, you're transferring a ridiculous amount of electrons. A very, very large amount, whether you realize it or not. Can somebody quickly calculate? Who has a calculator out? Divide, please, this number here. Divide this number by this number. You got to know how to use scientific notation and calculator to do this for me now. So 1e negative 6 divided by 1.6e negative 19. See what you get as a number. See what you get as a number. Got about a minute, so please try and get this. It's going to be tough on the on your iPad because I don't think there's scientific notation on there. 1e negative 6 divided by 1.6e negative 19.
I got 6.25 times 10 to the 12.
Wait, which one by which?
This one, he's got it right. It's fine. This one, this one. 6 point what?
25 times 10 to 12.
So think about how many electrons that is, guys. When you rub your hair with a balloon, you're getting this many electrons. 6.25?
Yeah.
That's how many electrons are moving. That's a ridiculous amount of electrons. That's this. That's how many electrons are moving when you rub a balloon on your hair. Isn't that incredible to think about? That's why it's so difficult to understand or comprehend things at an atomic level. It's not easy to physically understand this, so we have to use numbers that are really small to represent what's happening. The electron, the most fundamental thing as far as charge is concerned, is an extremely small amount. If you wanted to do a lightning bolt, take 350, which is the amount in a lightning bolt, and divide it by that number at the very top again. 1.6 times 10 to the negative 19. Whatever you want, if you want to know how many electrons are in any charge, just divide it by the charge per electron. So 350 over 1.6 times 10 to the negative 19. It's going to be much larger than this answer we just got.
1875
Times?
10 to the 21st.
Look at that. That's how many electrons are in a bolt of lightning. 2.18 times 10 to the 21 electrons. Yeah, move this decimal 21 spots. You're over here now. Okay, so do you understand what I'm getting at? Electrons are very small amounts of energy and charge that are being kind of put together. Hey, so here's the plan for Monday. You're bringing your work for Monday, and you're going to be working off your project. I will most likely finish this lesson to start Monday for like 10 minutes though. Okay, so be prepared to get right into your project after that. We were talking about, in the previous class, we talked about the electric charge on an electron and how it's quantized and how it's a certain amount. Now, we continue this lesson with insulators versus conductors. And if you know anything about electricity, we talked about getting electrocuted and stuff. What would you usually wear in your hands if you don't want to get electrocuted? Some sort of rubber-coated gloves. And those gloves prevent electricity to flow into your body because rubber is a very good insulator. An insulator is something that does not transfer charge easily. It can. If there's enough charge, rubber could actually melt right through or transfer through, but usually it's a good barrier. If any of you take the 86 subway stop and you come on the uptown side, if you got off the train today as you were walking up the steps, did you see rubber gloves on the right side? Those were electrical workman gloves. Somebody left them there. Nobody saw them? All right, I saw it this morning. I thought of this right away. There was 2 gloves there, and they were like white, knit gloves with like a brown rubber coating on the ends. Those are electrical gloves. I have a pair in there, but it's pretty much gloves that are dipped in a coating of rubber, and it causes the person not to get electrocuted if they were to accidentally touch a wire that shorts. A conductor is the opposite of an insulator. It does allow electricity. It conducts electricity. It's named accordingly. To remind you or to give you an analogous nature, an insulator that's a thermal insulator protects from heat transferring through. This is an electrical insulator we're talking about at the top here. Okay, but insulation has a word for thermal insulation also. So windows that are double pane prevent heat from going through. This prevents electricity from going through. But the word insulator could be electrical insulator or thermal insulator. We'll talk about thermal insulators later in the year, which you already kind of talked about in your chemistry courses. There are 2 other things to mention, and these are not on here. And these are things that are useful, but a little bit different, so I'm going to talk about them for a minute. The first is called a semiconductor. Anybody ever hear the word semiconductor before at some point in time? Semiconductor.
No.
Okay.
Oh, he's asking.
Yeah, do you know what it is? Go ahead.
No, but I'm assuming since it's semiconductor, it's basically just like a conductor, but not a full conductor.
Yeah, you're on the right track. And most people hear semiconductor, they think it's conductor and an insulator, or it's halfway in between. The idea is that this material can be a conductor with some variation of its material, of its temperature, of its atoms, but it usually is an insulator that can be turned into a conductor. Again, a semiconductor is usually an insulator, but you can kind of you can change its parameters enough to make it into a conductor. Semiconductors are extremely useful with computers. Because at certain times, certain parts you want to act as insulators, and other times you want them to act as conductors. The fourth term we're going to talk about is called a superconductor. Superconductor. Now, all things exhibit some sort of friction and energy loss. So even materials like copper, although copper wires are traditionally used in circuitry, when the electrons are flowing through that circuit, when electricity is being carried in these copper metal conductive wires, although they're conductors, copper itself is a conductor, most metals are, although it's a conductor, there is some energy loss. There's some charge loss along the way. There's something impeding the flow. Copper, although a conductor, does have some resistance to it. A superconductor is named because it conducts in a fashion that exhibits no resistance. So a superconductor is very useful because it would have like a zero friction or zero resistance in the circuit. You could apply some sort of a charge and it would easily flow through that circuit with no resistance. So a superconductor is a material that is a perfect conductor. A perfect conductor. And traditionally, it's cooled down to a certain temperature for this to work. In chemistry, you talked about absolute zero. You talked about the Kelvin scale. Kelvin. Remember, negative 273.15 kelvins. Celsius is really 0 kelvins. So this idea here of something being a perfect conductor can only really happen with super cool temperatures. Now, there are new materials that literally on like a daily basis, people are either making, I don't want to say inventing, but I guess inventing would be a good word. Yeah, inventing, but they're not discovering them. But they're making these new materials as a result of other materials that act like superconductors at a regular temperature. This is like a huge breakthrough because imagine if the electrical energy coming from power lines into your home had no resistance. You'd be getting all that energy. You wouldn't be losing any energy along the way. We wouldn't be wasting energy in a sense. So if everything could be made of materials that were superconductors, we wouldn't have to be worrying about any sort of loss in energy when that energy is transmitted from the power plant to your home. Going from the power plant to your home, a lot of energy is actually lost along the way. If none of that energy was ever lost, you'd be getting as much energy as possible, and therefore cost of energy would go down. Okay, so if everything was made of a superconductor, it'd be great. Now, materials that are superconductors are rare. And again, traditionally they have to be super cool down to temperatures of like 5 Kelvin, where it's like impossible to actually use that in real life. But they're coming out with more and more materials lately that can become superconductors at almost room temperature, which is really astonishing to think about. Because you don't have to cool it down to a certain temperature, so it can be like everyday materials that they could use. But they have to add things to them. They're really coming up with like, a mutation of 2 other materials together that are providing superconductive properties. It's not just one material that's being used. The recent one was, I think the recent one was solid hydrogen is actually one that they're looking into now. But anyhow, that's a whole other story. But these are all recent things that are becoming on. Let's talk about 3 ways of charging. The first one we already spoke about. You take a balloon, you rub your hair with it. What happens again? Who can remember from last class? Give me the specific what happens. Don't make a misconception here. What happens?
Well, the electrons in your hair are transferred to the balloon, vice versa.
Therefore,
one loses and one gains electrons.
Good. So one loses electrons, yielding a positive charge for that object, and one gains electrons, yielding a negative charge. So if you took that balloon then, right? If you took that balloon and stuck it to the wall, it's not the same idea, but we're going to actually see how that sticks to the wall in a minute with the third type. So the first type is just by rubbing it on your hair. So literally you rub 2 things together. I think, did we do this, right? Didn't we do this with Anthony?
Yeah.
Did Anthony do this with your class the other day? Yeah, it's the other class that did it yet. So you took like a rod, like that rod, and rubbed it with the cloth, the wool cloth, put that inside, it showed that there was charge or excess of electrons on the rod. That's charging by contact. So at least you guys saw this already. This is the next one, which is called induction. And it's not that difficult, but let me explain. You take that same rod that you charged, so you charge up the side of that rod again. You bring the rod that's charged So let's say I took the wool cloth, right? I charge up this rod. So now this rod has an abundance of electrons on it. I take this rod with an abundance of electrons. I hold it near a neutral source or a neutral body. Naturally, because this is negative, what charges want to go toward it? Because what happens? Because opposites attract. So when I hold this negatively charged rod right here, look, the positive charges come to the left, the negative charges go to the right. So as a result, what we're going to see here is when holding this rod, all these positive ones flow over here. Now, the second step to charging by induction is when this is still in the proximity of the actual neutral thing, connect a grounding wire. A grounding wire is literally a wire that would connect to the earth. So you connect a grounding wire. If there's a grounding wire, those electrons that are like hanging out right over here, they don't want to be anywhere near this rod because like charges, what do? They repel. So these negative charges over here, they want to flow away from this. So naturally, they take the path of least resistance and they just flow right out into the ground. So the electrons are flowing out of the wire into the earth. Now, as a result, this eventually becomes positively charged because of not a gain of protons, but a what? A loss of electrons. Very good. Well done. So the electrons are the extra negative charge that's still here that wants to be moving away from this rod. They flow out of here, leaving only positive charges. So this is what you're left with. All the electrons flew out. Now you remove the grounding wire, and then remove the rod, and you're left with what's over here in scenario D. So this is called charging by induction. So you charge this up, bring it to the object, ground the object, the electrons flow out, remove this, what are you left with? A lack of electrons. A lack of electrons you're left with, yielding a net positive charge on this apparatus.
So if you induct products to get a certain charge for them?
Yeah, so if you needed to get something to be positively charged and you couldn't do it by contact, induction is used a lot.
So why would you want a positive charge rather than a negative charge for something?
Well, maybe you're helping to if you're at a manufacturing industry where you're making things magnetic, ferromagnetic materials, you want them to have a magnetic charge, you might do it that way. But in this case, this would be like an example where, let me think, why we want a net positive charge on a sphere. I mean, this is just an experiment that was done. That's the way induction works. Induction is used, if you charge your phone, that's using induction. There's no actual touching that's occurring. But the energy is actually flowing using induction. It's a different type of induction, but uses the same principle here, that they actually don't need to be in contact. Let me think on that. Maybe I can give you an example of when you would do this. Gabe, you had a hand or no? You're just doing your hand? Really? Okay. Last slide is called polarization. And this is one that you've seen more often. This is the balloon, really. So for the balloon first, you rub the balloon against your hair, so you're charging by contact. But then, if you take that same balloon and hold it against the wall for maybe, 5 seconds and remove your hand, what happens to the balloon usually? It sticks to the wall. How is that happening? Well, this is what's happening right here. So the balloon is the charged object on the far left. You take the balloon that's already been charged because a lot of the balloon electrons jumped onto your hair. So the balloon only has positive charges left in it. You take that balloon and you bring it near some sort of another material. What's going to happen from your chemistry class, if you remember, is that all of these molecules are dipoles. Remember dipoles? You have a positive or negative end of your molecules. So usually they're oriented in some arbitrary fashion. But what will happen is the molecules near the surface of this whiteboard will actually realign themselves in the presence of that balloon. So when you bring the balloon near it, it causes all the negative charges to kind of come to the surface. See how this insulator, the wall, the whiteboard here is an insulator? Suddenly, those molecules realign themselves so that what? So that you have opposites touching each other, because opposites attract. So when that balloon sticks to the wall, what's happening is it's causing the wall molecules to realign themselves, and as a result, they stick together. Same thing happens with your hair in a comb. If you've ever combed your hair before, and then you take that comb, put it near, and this will actually work, put it near a couple of sheets of paper, it'll literally pick them up off the ground. Because paper is an insulator, its molecules will realign like this. Your comb is charged with an abundance of electrons. It'll cause these molecules to realign, making the dipoles all orient so that they stick to the actual comb. So this is called polarization. Polarization. Okay, you're taking a charged object, bringing it near an insulator, and causing the insulator to realign itself. Are you giving the insulator a charge? No, you're not. Let's make that clear. The last example, with induction, that sphere ended up with a net positive charge at the end. Here, look, this is the material, this is the insulator. It's not changing the amount of charge. It still has, for every positive charge, it has a negative charge. For every positive charge, it has a negative charge. So these are still related to one another. For every positive, there's a negative. But they're realigning themselves. You're not losing or gaining charge out here. So the three types are charging by contact, where you literally aggressively rub two things together, and electrons, one of them gets positive, one gets negative. Charging by induction, where you bring it near, ground it, comes out. And then charging by what's called polarization, where the insulator just reorients itself. It's kind of like you're charging it, but you're only charging the local area of the surface. So by bringing the balloon near the whiteboard, only the molecules on the very surface are realigning. Everything else is still the way that it was previously. All right, that's it for this section. You have a couple questions about 4 or so.
19.2
Yep.
was on. 19.2 was on.
This is just 19.1. We're about to start 19.2 right
Yes,
now.
it is not on